Okay, so hello and welcome to another video involving for Math 251. So this is going to talk about graphing rational functions. So previously we talked about limits, both at infinity as well as limits that approach infinity of functions that are in the form of fractions, which are rational functions. Now we are going to be talking about what these graphs actually look like and how those limits relate to the graph. As you go through this, I would encourage you to follow along. So for this first one, I would encourage you to pause the video and graph this function on Desmos, and then see if you can answer the limits that are to the right. Okay, so if you graph the function on Desmos, this is about what it looks like. Something I would encourage you to do is I would encourage you on Desmos to click on the graph where x is equal to 0. So click on the graph right at this point. You should see on Desmos that it is an open circle and it tells you the y-coordinate is undefined. So we're going to talk about this more later. This is what's called a removable discontinuity, or sometimes referred to as a hole in the graph. So this is a feature of some rational functions. Then where it splits, so where it splits down here and up there, this is what's known as a vertical asymptote. There's another vertical asymptote over here at x equals 3. So now let's go ahead and let's use this graph to calculate these limits. Please note that in the previous video we did calculate these limits algebraically. This time we're just going to use the graph. So for this first one, for the limit as x approaches infinity of this function, so infinity would be to the far right. If we look to the far right, it looks as though it's approaching 0, so this limit is 0. Now, for the limit as x approaches 3 from the right of this function, so here is x equals 3. So if we are approaching 3 from the right, it is going down forever. So this limit would be negative infinity. If we're approaching 3 from the left, so that would be right here, and we end up going up forever. So this would be positive infinity. And then, as much as we have an open circle at 0, if we use Desmos and we look at the points nearby it, this ends up being approximately 1.33. In case you're wondering, the exact value of it is 4/3. However, we're not doing the calculations. Instead, we're using the graph. And if we click on the exact point where x equals 0 on this graph on Desmos, we will get an undefined value. So we will never see the value 4/3. So now let's talk about some of the terminology in this graph. For rational functions, we come across two key terms that affect the graphs at particular x values. So one of these is what's called a vertical asymptote. So in a vertical asymptote, one or both sides of the graph go to infinity at a point. So you can have a vertical asymptote where one side goes to positive infinity, the other side goes to negative infinity, or both could go to positive infinity. And another one that's worth noting is that both also could go to negative infinity. So each of these is a case of a vertical asymptote. For other functions, you may have a situation where only one side, either left or right, goes to infinity. However, that doesn't generally come up with rational functions, meaning a function on the top of the fraction, a function on the bottom of the fraction. Another thing that comes up with rational functions is this idea of removable discontinuity. So if we take the function x squared plus 4x plus 3 over x minus 3, if we plug in 3, so 3 squared is 9, minus 4 times 3, so that's 9 minus 12, that's negative 3, plus 3, the top is 0. On the bottom, 3 minus 3 is 0. 0 over 0 is undefined. So we do not have a point on this graph for x equals 3. On the other hand, if we were to take the limit as x approaches 3 of this function, we can factor this whereas we can factor the numerator, what's on top, and then cancel. So doing that and plugging in, we end up getting 2. And what that means is as x approaches 3, y approaches 2. Now, the point itself is not defined, so for that reason we put an open circle. This can be thought of as removable because if we were to fill in that circle with another point, then the function would be continuous. That's unlike an asymptote where we can't remove that discontinuity. There's no way to bridge infinity. So, these are the two main concepts that we will be dealing with when it comes to rational functions. So, we'll start out with identifying vertical asymptotes, because this is where we are looking at a function splitting to infinity and negative infinity, and these stand out on a graph. These are something that we want to know where they are on a graph, and we want to be able to sketch them accurately. So first of all, because a vertical asymptote involves plus or minus infinity, that's going to be 1 over 0 slightly less, or 1 over 0 slightly more. And of course, it can really be any number, but just 1 over, we'll deal with it for the moment. So, in order to have this, we need the top to not be 0, and we need the bottom to be 0. So what we can do is we can reduce this expression by factoring and canceling common factors, and then we can set the denominator, whatever's in the bottom, equal to 0 and solve for x. If we do this, this will help us identify our vertical asymptotes, and then we can take the limits. If we take the limit on each side, we can decide whether one side is up and the other is down, whether both are up, or both are down, or it's a flipped version of this. So, that's what we're going to do next. So, let's start out with this. So, for this first function, we have y is equal to 1 over x squared minus 7x plus 10. In this case, there's no way to reduce the fraction, so we can go immediately to canceling out, or immediately to setting the denominator, the bottom, equal to 0, and then identifying the x values of vertical asymptotes. So we start out with x squared minus 7x plus 10 is equal to 0. You can solve that in any number of ways. So I'm going to put, for me, the way to solve this would be to try to factor first, which this factors nicely. So this ends up factoring to x minus 5 times x minus 2 is equal to 0. We can then set each of these equal to 0. first one, we add 5 to both sides to get x is equal to 5. The second one, we add 2 to both sides to get x is equal to 2. So those are our two vertical asymptotes. Now, for this particular problem, I'm also asking us to sketch the area nearby. So to do this, we're going to need to take the left and right hand limits of each one. So let's start out with the limits from the left and the right of as x approaches 2. So taking the limit of this function. Now, for these left and right hand limits, it's often helpful to write the factored form. So I'm going to go ahead and I'm going to factor the bottom as I did in solving it. So now, if I plug 2 in for that, I'm going to get 1 over, so 2 minus 5, and the negative just means it's slightly less than 2. So 2 minus 5 is negative 3. And then slightly less than 2 minus 2 would be 0 with a minus. Now, a negative times a negative is a positive, so this is going to be 1 over 0 with a plus, which gives us positive infinity. So to the left of 2, it goes to positive infinity. On the other side, for the limit as x approaches 2 from the right, it's a very similar process. So from this process, I found that as we approach 2 from the left, it's going to positive infinity, and as we approach 2 from the right, it's going to negative infinity. So around x equals 2, we can sketch it as being something like that. Now, it's a similar process for x equals 5. It ends up being the reverse of that. So to save time, I'm not going to show it in the notes, in this notes shown in this video. The notes that I post online will show the process for that. Now, let's move on to the next function. Okay, so for this function, this can be further reduced. So to reduce this, I note that for the bottom, both x cubed and 4x squared have x squared in common. So I can factor out an x squared from both of them and end up with x squared times x plus 4 on the bottom. Now, I can always write something as 1 times whatever I have. So on the top, I'm going to write it as 1 times x plus 4. And then cancel the x plus 4's. This gives me that this function is 1 over x squared if x does not equal negative 4. Noting that if I plug in negative 4, I will get 0 over 0, which is undefined. Now, this reduction helps me in vertical asymptotes because this gets rid of situations where both the numerator and the denominator are 0, which do not necessarily result in vertical asymptotes. As a matter of fact, for any factors that cancel, 0 over 0, so long as nothing is left in the denominator from it, will not be a vertical asymptote at all. Now, here I set my reduced denominator equal to 0. Which, solving that, gives me a single solution at x is equal to 0. So to see what it's doing around, I do the same process I did with the other one, and that is I take the limit of the function from the left and from the right of my value, which in this case is 0. In the case of limits, I'm almost always going to want to reduce any rational functions I have, so I've reduced it to what I had before when I previously reduced it, and that is 1 over x squared. So plugging into that gives me 1 over 0 minus squared. Noting that a negative times a negative is a positive, this becomes 1 over 0 plus, which is positive infinity. A similar thing happens with 0 plus. So again, factor and reduce it. If I plug in 1 over 0 positive squared, well, positive times a positive is still positive. And then 1 over 0 positive is positive infinity. So in this case, both sides go to positive infinity. This means that around x equals 0, which by the way I realize is the y-axis, both sides will go up. And this will then give us a two-sided limit. The limit as x approaches 0 of this function is infinity. Okay, the next item is removable discontinuities. So as a general rule, rational functions will have a removable discontinuity when both the numerator and denominator are 0. Although there is a key thing to that. We have to make sure that after we have canceled, whatever x value does not still make the denominator 0. So our check for after canceling is to take the limit at that x value and make sure it isn't infinity. So our general process for identifying removable discontinuities is to, first of all, factor the numerator and denominator. Then we're going to cancel out factors. For any factors that cancel out, we're going to set those equal to 0 and solve for x. Then to guard against asymptotes that are apparent in common factors, we're going to take the limit and make sure the limit isn't infinity. If the limit is infinity, then that x value is not a removable discontinuity. Instead, it's a vertical asymptote. If the limit is a number, then that tells us where our removable discontinuity point is, and it tells us the height at which to put the circle on the graph. Okay, so let's identify some removable discontinuities. So let's start out with this first function, y equals x squared plus 9x plus 14 over x squared plus 10x plus 21. Factor in the top gives x plus 7 times x plus 2. Factor in the bottom gives x plus 7 times x plus 3. So the factor that cancels is x plus 7, and that's what we want to look at for a removable discontinuity. So we set x plus 7 equal to 0, which gives x is equal to negative 7. Then, to ensure that this is not an asymptote and is indeed a removable discontinuity, we then take the limit as x approaches negative 7. So, taking this limit, similar to what we did previously, we're going to factor the top and bottom and simplify prior to plugging in negative 7. So then, once we have factored and simplified, we'll plug in negative 7 to the reduced expression. which gives us negative 5 over negative 4. First of all, that is an infinity, so this is indeed a removable discontinuity. It also then tells us the exact coordinate of it. So, in this case, our removable discontinuity is at negative 7 and then 5 over 4. Note also that a negative divided by a negative is a positive, so we don't need to write the negatives on the answer. Now, let's move on to the next problem, identifying removable discontinuities on the function x squared plus 9x over x times x minus 1 times x plus 9 squared. So the first thing to do on this function is to factor and simplify. The top factors to x times x plus 9, and then the bottom is already factored for us. From here, we can cancel the x, we can cancel the x plus 9, and we notice that the top is times 1. Or actually, since the bottom is x minus 9 squared, when we cancel the since the bottom is x plus 9 squared, when we cancel the x plus 9 on the top, it only cancels the exponent for the x plus 9. Because again, we had two of those on the bottom, and only one of those cancels. So, from this, we can then set x equals 0 and x plus 9 equals 0 as our possibilities for removable discontinuity. So the first one is solved for us, and the second one, subtracting 9, gives x minus 9. We now need to take the limit of the function at each of those values. Using a similar methodology to what we have done earlier, we use the reduced form of the function to calculate the limit as x approaches 0. Doing this results in 1 over x minus 1 times x plus 9. Plugging in 0 gives 1 over negative 1 times 9, which is negative 1 over 9. So, from this, it is confirmed that the point 0, comma, negative 1 over 9 is a removable discontinuity. The next thing for us to consider is x equals 9, or x equals negative 9. Using a similar process, we come to taking the limit of the simplified form of the rational function. Now, here is where we run into an issue. The numerator is 1, the denominator is negative 10 times 0, since negative 9 plus 9 is 0. So that results in 1 over 0. Well, 1 over 0 will be plus or minus infinity. Because plus or minus infinity is not a point on the graph, but rather represents the function going forever up or down, x equals negative 9 is not a removable discontinuity, and instead x equals negative 9 is a vertical asymptote. So we have now shown how to calculate vertical asymptotes as well as removable discontinuities. That is all for this lesson. I appreciate you watching this video, and I wish you all a happy Thanksgiving if you have watched this before Thanksgiving, and if not, I look forward to seeing you next week.